Okay, welcome to everybody. I think now we can start. First of all, thank you to everyone to attend today's event organized by the Artificial Intelligence Student Society. I am Andrea Gasparini. I'm the president of this association currently. Today, as we all know, we have the privilege of Professor Andrea Cavallaro at the Queen Mary University of London, who will talk to us about adversarial attacks and ethical implications. And after that, we will have one of our PhD students, Ginevra Carbone, who will give us an introduction to Bayesian neural networks and robustness of the models to adversarial attacks. I will pass on straight away the word to our guest, but first of all, we have another special guest, which is the coordinator of the Data Science and Scientific Computer Coordinator, and Professor Bortolussi, most of you know him, who will give us an overview, a quick overview of what will be in the future, the new activities of UnityS in the field of machine learning and artificial intelligence. Professor Bortolussi, are you ready?
Of course, always. So thanks, Andrea. I have to say that I'm very happy to be here, not just for the event itself, interesting, but in general for the existence of this event that is happening because there's a lot of students which are very committed and have a lot of fun in doing their activities and not only studying but also learning different ways. And this association is a great I would say spin-off of the master in data science and scientific computing. So I'm very, very proud of you guys. So what's happening here in Trieste then? Well, fundamentally, all started in a sense 4 years ago with the beginning of the master in data science and scientific computing, which is a master program, international, and actually jointly organized with CISA, ICTP. There's also University of Udine helping, and we also have now our Science Park and enough as teaching partners. Some companies like Esteco are providing courses. So it's a big initiative, I would say, of the university, but it's a big initiative of the system of research of Trieste, which is, as you know, one of the most rich, at least in terms of density, of institutions and, in fact, even of researchers in Italy and in Europe. So this master was studied and quickly, I would say, from second year on, in a sense, took over. The number of students is good for the University of Trieste. Is increased all the years, and we are about this year we have about 50 students. And master has 3 curricula. There's one in data science and applications, one is in computational science and engineering, and then from this year we also have a curriculum in artificial intelligence and machine learning, which is more dedicated, let's say, to machine learning and its applications and different facets of it. This is already great, but no, we're not happy with just this. So we moved forward, and since this year, we also have a bachelor program in artificial intelligence and data analytics, which will be naturally providing part of the inflow of students in the master program. So we still want to have students with different backgrounds merging and contaminating each other, which is a lot of fun, I think. It's what's happening in the master now. So if you're a physicist, a mathematician, a statistician, an engineer, you're very welcome, and you will still remain very welcome. But so this already gives you 3 + 2 years of formation in this area. But no, we're not happy with that, and there will be something new starting next year in 2021, which may be of interest to all of you, which is a PhD program. So there's going to be a PhD program in applied data science and artificial intelligence. So a program a little bit more focused on, say, on artificial intelligence and data science and their applications. So there will be theoretical research going on, and let's say applications, so connections also with industries and other research institutions in the area. With likely there will be 3 curricula within the PhD program focused on let's say 3 different branches of application. So one will be Industry 4.0, smart cities, smart transportations, and hard sciences, whatever it means, so applications in science. Another one would be more focused on medicine, life sciences, environment. Third one, more focused on economy and society. So depending on your taste, essentially there's everything for you, and theory will be spread throughout all these curricula. So that's the idea. It somehow follows a bit the structure of the Italian National Program on Artificial Intelligence, which is also going to start in 2021. And also there, I mean, we as the University of Trieste, we are trying to participate. We will. So we will also be involved in this national program, PhD in Artificial Intelligence. And well, I would say this is more or less it for the moment, which is already quite a lot of things going on. So if you're thinking about, maybe a PhD or maybe a PhD done within a company, though, so more on applied research, now there is a sensible chance for you here in Trieste. And with this, I would say what we have, I'm kind of completing this. The more things will happen in the future, I think, but for the moment, we are happy with what we are having here. So what's going to be the next step? Well, next step is actually today to enjoy what's going to come next. So there will be Professor Cavallaro and then Ginevra talking a little bit about adversarial examples, as you know. The deep learning is, changing a lot the landscape of artificial intelligence and making several things, several applications which are essentially impossible just a few years ago, actually now possible and more or less already on the market for some reasons. But there are some concerns about the reliability of this technology, and some of these concerns are intrinsically connected with the technology itself. I mean, with deep learning itself, with neural network itself, with the mathematics behind, with the actual tools that we're using. And adversarial examples are, adversarial attacks and adversarial examples play a big role in this respect, because they make whenever they actually are there, they make this technology intrinsically vulnerable to cyber attacks and to so a bit fragile to be used in safety critical applications. So solving these issues or ameliorating these issues or making these issues less significant is an important research topic, something we are also working here in Trieste in collaboration with colleagues in CISA, actually. So I think that you will get better feeling of this in the next 2 talks. So thanks for the attention. Sorry for not having the slides running. I just was too optimistic with respect to Microsoft. And thanks for, I said, for the attention, for having this great student association letting me speak. Just greet you at the beginning. So, let's the second part of the deep learning day start.
Okay, thanks, Luca Bortolussi, for the introduction. Without further ado, I will leave the work to, I will pass on the torch to Andrea Cavallaro. He's a professor at the Queen Mary University of London, and he'll talk a bit about adversarial attack, touching on some social ethical implication. So, thank Andrea for being here, and whenever you wish, you can start.
All right. Thank you, Marco, for the introduction. Can you confirm you can see me and hear me well before I start sharing the screen? And are you still seeing the presentation?
Yeah.
Okay, great. So if anybody would be kind enough to maintain their video stream on so that I can get an immediate feedback, that would be appreciated. I can see, I think, 1 person at a time. That would be great for me. Anyway, good afternoon. And thank you very much for having me in your event today. It's great to hear so many interesting activities going on in Italy, and in particular in Trieste. What I'll be talking about today is classifiers, which are used now in applications we are interacting with every day. So probably if you have an iPhone, you might use AI between 50 and 70 times a day when you unlock your phone. If you're using Netflix, you get recommendations about films to watch. If you're using a spell checker, certainly they're using AI behind the scene. If you're using a spam filter, which I'm sure you are, then AI is playing behind the scene. So there are a lot of very successful applications of deep learning classifiers. However, those classifiers have got some vulnerabilities, and today we will talk about those. But before starting, let's see what a classifier is in the context of today's presentation. So what you see there is a box containing an artificial neural network that we usually train using a substantial amount of training data with a certain training process, which is now a mixture between a science and an art. And the idea then is, once the classifier is selected in terms of architecture and values of the parameters of this architecture, you provide a certain signal in input, and you obtain a classification result. In the specific case of today's presentation, that classification result will be a categorical variable, a one-hot vector that represents a label for the signal. And today we will talk as a signal about images. What we are interested in is about the robustness of this classifier M. And for robustness, I mean the ability of the classifier M to be able to provide the same label Y if we have perturbations in the input signal X. And in particular, we will see two applications of robustness. One towards the end about AI applied to self-critical systems, so systems who are capable of taking decisions in real time and must be robust. But what the presentation will focus on today is particularly the ethical aspects of AI. So a lot of companies, a lot of applications are probably moving faster than the norms, the legislations, and the rules we use to govern them. And therefore, at times, it might be better to equip a user with the ability to protect their own data. And that's what is the focus of the presentation today. We will exploit the vulnerabilities of deep neural networks in order to protect the privacy of individuals. And in particular, we will be looking at adversarial examples, which are intentionally perturbed signals that are capable of misleading one or more classifiers. What does this mean? Well, if we have an original signal, for example, an image you might want to share in a social media platform, then that image will generate a certain class label. Say that image was taken at the seafront in Trieste, for example. Then we want to be able to create this adversarial signal, this adversarial image, X dot, such that the resulting classification is different from the original one. So if at the beginning it was a nice image of the seaside in Trieste, maybe the resulting classification result of the adversarially perturbed image will be maybe it's in the mountains somewhere in Colorado. And what we are interested today is how we craft these adversarial signals in order for us to protect those characteristics of the image when we don't want those characteristics to be automatically inferred by classifiers of any type. So why do we care about this? Why do we want to mislead classifiers? It seems to be an inappropriate activity to do. Well, you're probably all aware of the amount of data we are sharing. Those data are used for a number of applications. For example, if you share your images in Instagram, in Facebook, you would have faces of people that are detected and then labeled according to the identity. And that's certainly for some a good service in order to alert your friends of the type of images you have shared. However, on those images, either a service provider or a third party could extract additional information. Some of this additional information will be used to improve the service. Some other will be used to generate a very detailed profile of a user in order for that user to be targeted very specifically with information. And that information could be desirable information like advertisements for products people are interested in, or information that is aimed at modifying the behavior of people, for example, in the political arena or in other important aspects of today's life. So what we are focusing on today is how the user, the person on the left, will be able to keep on sharing their data, in particular images, in order for them to be able to enjoy services without the data to be breached in any form. And in particular, we will consider the example of image sharing in social media, where the objective is to share information and images with our friends in order to engage them in our experiences. And we know that even if the objective is for those images to be seen by humans, that behind the scene, there are a number of classifiers that are looking at whether the content we are sharing is copyrighted or is inappropriate. And of course, these are inferences that we accept as part of the free service we are obtaining. However, behind the scene, there could be additional classifiers working, and those classifiers could be looking at the type of scene is depicted. Maybe a person is often going to a synagogue or to a church or to a mosque, and might not want to share that information with a third party. Information about age, gender, emotions, and the relationship between people who are on those pictures. And certainly, we are probably questioning whether those type of inferences are done through a proper informed consent on the side of the user. And so let me spend a few slides now talking about consent and this importance of data that is shared today in ways we were not used 20 years ago, probably even 15 years ago. So consent and personal information are two very important concepts here in Europe. They are regulated by the GDPR. Consent is meant to be freely given, specific, informed, and unambiguous indication of the data subject wishes. Data subject is ourselves. And personal data is then any information relating to an identified or identifiable natural person, which is the data subject. So these two concepts are very important with respect to the use of images. And at the introduction today, the terms ethical AI have been mentioned, and this is part of this very important and growing area of applying machine learning, and in particular AI, in a way that is in line with what our values are. Now, why do we care about this when we're talking about AI? Well, it's because we do have possibly some substantially contrasting objective at the moment. We have the user on one side and the machine, a service on the other side. The user must provide consent, and that consent must be informed as defined previously. And the data about the user should be minimized. What does that mean? Well, it means that data about a person, a data subject, should be adequate, relevant, and limited to what is necessary in relation to the purposes for which they are processed. So any additional inferences that are not agreed upon by the user should or must be avoided. But why those inferences are desirable? Well, they are desirable because we are receiving a lot of free services, and a way to make sure that those free services are reaching the users is to extract added value from the data. So there is this contrasting objective of respecting the privacy of a user, and at the same time extracting information that is valuable for the companies who are providing us with a service, but also additional companies that can take advantage of the open source data that are shared on social media. So there is this contrast, and this contrast gives us the opportunity to try and exploit the characteristics of classifiers in order to defend the rights of a user. So what we are talking about is the situation in which a system is optimizing its behavior and its information flow towards a user that is both the source and the target of a process. And we want to protect the user from undesirable inferences, meaning we want to defend a user from machines that are automatically extracting information that then is used to generate profiles about these users. And in particular, what we will be talking about today is how we can learn manipulations to protect the privacy of people while keeping on enjoying the services that are available today. So we want to protect the private content of images from automated inferences that are not desired by the user, for which an explicit and informed consent was never given. And what you will hear quite a lot when people talk about privacy is that utility and privacy are contrasting objectives. And what I'm trying to convince you about today is that utility and privacy can go hand in hand. So the utility is using a service at a level of service which we are happy with, and privacy is protecting the personal information of a data subject. And I will show today how it is possible to protect privacy while maintaining the utility of a certain service, something that in a number of situations have been shown not to be possible, but in the specific case of images I will show today, it is possible and desirable. Before starting, I'd like to clarify some definitions about the classifier, so M, which we have seen earlier. So a classifier is said to be a white box classifier when we have full access to its architecture and its parameters. On the other hand, it's said to be black box when we haven't got information about the architecture or the parameters of that classifier. And the only thing we can access is either the resulting soft label, meaning the probability for each of the categorical classes that the classifier was trained upon, or the hard label, the decision, the final classes of interest, or we could even have no label at all. For example, whatever image you pass on in any free service will be parsed by a number of classifiers, but we don't really know unless we are expert what type of inferences are done in there. So in the case of the black box, we will have access to, of course, the input data we provide and one of those three approaches. And we will see how we can generate adversarial attacks in cases where we have a black box scenario. And the black box scenario is also a scenario that allows us to query a classifier and seeing the output of that classification results for a large number of times. So if we want to design an adversarial attack for these good purposes, what should be its properties? Well, the first property is its effectiveness. So we want it to be successful in evading a classifier. And this can be done in a targeted manner, meaning that we are forcing the classifier to identify a certain specific class we want that classifier to detect, or untargeted, meaning that we want the classifier not to detect the original class. The second property is the robustness. Here is the robustness of the attack, not of the classifier. In this case, we want the attack on the classifier to maintain its properties, even if the classifier uses some forms of defenses. And the third property, a very important one, is transferability, meaning that if I train a perturbation on a classifier, then the very same perturbation should be effective in another unseen classifier. And specifically, when we're talking about privacy, we want these modifications not to be detected. And even if they are detected, we don't want automatically the system would be able to recover the original class. So these are 5 properties that we will mention while discussing the various approaches. And I will then share the slides with the organizers. So if some of you are interested in diving into some of the work we have done in the past couple of years, you can follow those references. These are recent methods we have proposed in terms of evading classifier for privacy purposes, and what are also the problems associated with classifier. And in particular, the second work, which I will mention at the end of the presentation, is about robustness for autonomous vehicles, so self-driving cars. Let's see the first method that we developed. It is a method that we called a private fast gradient sign method. This method is an evolution of the state-of-the-art fast gradient sign method, which we modify in order for the class the classifier was pushed to detect was such that it was not the ground truth class. We haven't mentioned yet what the ground truth class compared to the original class, and I think now it's the time to do so. A classifier, by definition, will not be 100% correct, and therefore, if we are generating an adversarial attack, we have to make sure that flipping, when we are changing the results of the classification, we are not actually pushing that classifier towards the correct class. And therefore, we need to be sure that the class we are pushing the classifier towards is with high certainty not the original class, because we have the original class, which is the one detected by the classifier, the ground truth class, which is the ideal class, the adversarial attack is pushing the classifier to detect. And considering the original class, we don't want the original class to be flipped by chance towards the ground truth class. And in order to do that, we select our target class, y tilde, there on the bottom right, in a way that we will mention later on, that is reducing the probability that that class is the ground truth class. And in particular, the way through the fast gradient sign method we are looking at generating the adversarial perturbation is by using the gradient of the cost function with respect of the image. So when you're doing backpropagation with deep learning, you're changing the value of the parameters based on the pair annotation and input signal. In here, you are keeping fixed the value of the parameters, and what you're changing are the values of the pixels. So you modify each value of the pixel by plus minus epsilon in there, based on the gradient with respect to the image itself. So we are modifying the value of the image in order for the classifier to go towards our target class. So the perturbation, as you're seeing in the equation on the bottom right, is constrained by epsilon, which is usually 1 or 2 quantization levels of the image. And the goal there is to maintain the visual quality of the image. We don't want, in this case, to have very large perturbations. It's a targeted approach. So it's an approach that goes towards a specific class. And again, I will mention later how this class is detected. And it's an iterative method that it iterates until a certain classification probability is achieved. And in this case, because we are using the gradient of the cost function, this is a white box attack, a white box method. So let's see one example of result with this approach. So on the top there, you see an image X, the original image. And on the right, you see the manipulated image, the image X dot. I hope that you agree with me that those images look exactly the same. Well, despite those images looking exactly the same, the classifier M, the same classifier, generates 2 different labels. The image on the left is classified as a church in terms of what scene it depicts. The image on the right, surprisingly, provides as output, with the same classifier, the label Zen Garden. So we were in here successful in maintaining the quality of the image, the perceived quality of the image, while changing the label. And because we could manipulate the probability of the classification for the specific M, we actually made the classifier even more certain that that image was a Zen garden as opposed to a church. So you see in here that if we have access to the classifier, then we can manipulate the input in such a way that the classifier is wrong and feels very confident in this wrongness. So here is a first example of how we try to protect the privacy of images, in this case, our religious beliefs, when we share them online, to avoid a profile of ourselves being built based on the type of images or the type of place we tend to visit. However, these type of perturbation are high frequency spatial perturbation. So we are changing each pixel at a time, trying to slowly, with each iteration, modify the image to go away from the original class. So if you see the top left image there, in the bottom row, you see 4 different adversarial methods and the type of perturbation they generate for those images. And you see that all of those are high spatial frequency perturbations. So this is the type of noise that is added on the original image. Here is amplified so that you can easily see it on the RGB channel of that image in order for that image to be misclassified by the classifier M. So if I would tell you, hey, how would you defend the classifier from an attack like this, you probably would say, well, that's very simple. I will take the input image. I would assume that that image is always perturbed. Before passing that image through my classifier, I would use a low-pass filter, a median filter. There is very likely to flip back the class to the original one. So this type of perturbations that are generating high spatial frequency noise are not robust to defenses, and they tend to be defeated by a simple low-pass filter or a simple JPEG requantization. So the 2 properties we were interested in, the first, the robustness, the second, the transferability, because this type of changes in the input in the image are not likely to generate an error also in other classifiers. So we looked at ways in which we could transform this private fast gradient sign method into a robust method. And the way we went about this was to, instead of using a simple classifier to generate the perturbation, we used a set of classifiers and also a set of defenses that were used in each iteration in order to create a modification of the input image that was more transferable and more robust to defenses. So the way we went about this was to generate, again, an image that was moving in the direction of the gradient with respect to the image, but for each iteration, we changed randomly which classifier we created the adversarial attack for. But not only, also before generating that perturbation, we passed the image through a defense. So we had a set of defenses that are known. And so we select at each iteration one defense and one classifier, and we keep on modifying the image until we are successful in our misleading objective. And what I'd like now to spend some time on is on how we can, in the targeted attack here, generate an image that is unlikely to be the image of the ground truth. So the way we go about that is by ranking the probability of all the classes. So imagine you have 365 possible classes a classifier will be able to detect. We sort and rank those probabilities, and we consider all those, such as the cumulative probability distribution, exceed the threshold. And that threshold allows us to move away from a classes that could contain the ground truth class, which is close usually to the original class that is detected by the classifier. So D is the number of classes, and we sort those classes and we try and go away from the original, of course, but also for the potential ground truth class in case it doesn't correspond to the original. I just want to give you here an example of what are the classes. In the case of a set of 365 classes, these are from the Place 365 dataset. And you see in here our specific choice of gamma that allowed us to have a median number of classes 307 to randomly choose from to decide which was the targeted class we were going towards. And I'm going to show here some examples of results. So in this slide, you're seeing the original images and their estimated class. In the next slide, I will show you the modified images and their corresponding class. So the class that the same classifier as detected. And you will see what type of noise has been added to those images. Here we are. So you see that all the 9 labels had been flipped. and some noise had been introduced in those images. Those images are still intelligible, are of decent quality, but despite representing an obvious scene, you see that the label was changed by the classifier. And this perturbation is stronger than the previous one, and the strength is the cost to obtain an adversarial example that is transferable across classifier and robust to defenses. So with this type of approach, we pay in terms of visual quality, but we gain substantially in terms of robustness and transferability to other classifiers. We talked about this amount of perturbation that we use to create an adversarial example. There are two types of approaches. The constrained one, which is the one we mentioned so far, where we have small, usually norm bounded with the L1, L2, L infinity norm. These, unless we are using the type of approach we mentioned earlier, they are usually with limited success with unseen classifier, and unless we are using the approach we mentioned earlier, they are vulnerable to defenses. And there is another family of perturbations, which are unconstrained perturbation, meaning that we are not trying to limit the modification around a ball, around the point in the image space represented by the specific input image, but we are trying to modify the image much more. And I will show you an example of method that we have developed in this area. So some of the methods prior to ours were trying to transferring new texture in the image. Of course, if you have an image, you start pasting some different type of textures, you are more likely to mislead the classifier. But what we wanted to have is an image that looked very similar to the original one. And actually, if it is not shown side by side to the original image, then would be an image that seems to be natural. Then other authors looked at how to shift randomly hue and saturation value or recolorized the images. And these are the type of results they obtained. So you see that, for example, the image in the middle and the image on the right are not particularly appealing and are not really the type of images you would like to share. So when we saw this works in the state of the art, we said, okay, maybe we can do better. We can do this type of large-ish modifications, but at the same time we can modify those images. And that is the method we presented earlier this year at CVPR that we called Colorful, which is a content-based black box adversarial attack. So in this approach, instead of treating the image as a whole, we consider the objects that are composing this image. And in particular, we assume that those objects might undergo different types of color changes. For example, vegetation will be changed in a certain color interval, sky and water will be changed in a certain color interval in order for them not to appear synthetic or wrong. If we detect a person, then we don't do any change at all because our human visual system is very sensitive to any changes in, for example, skin color. And so a person, we don't do anything, vegetation, sky, and water. When we detect that class, we modify them in a certain interval. And if there is another class instead, we just modify it as much as needed to flip the results. And we selectively modify that, therefore, the colors. And we use in particular the LAB color space for reasons that we will see later on. And let me show here an example of image X on the left and image X prime on the right. You see that the image is perfectly the same except for the color of the background, but just changing the color of the background allows us to trick the classifier into estimating the wrong label. So you see it's a substantial difference in label while having changed only the color of the background. So all of you who are interested in the robustness of the classifier can certainly use this type of approaches to study how to make classifiers more robust. Here we have changed just the color of the background and we succeeded in defeating the classifier. How does this method work? So you have the image on the left. We apply semantic segmentation. There are plenty of very effective methods now to segment an image into its component objects. And we detect the various classes we mentioned earlier. In this case, we detect a person and the background. And we apply a color perturbation, particularly only on the ABN component, so the chrominances of the color space. We don't touch the luminance, and we modify only the chrominances, in particular in the A-B color space, where we can nicely control perturbation with respect to the human visual system. And then we recompose back the image and we generate the new one. We check whether the classifier is misled. If not, we try another modification with a smart way of randomly selecting the new colors. And one of the advantages of this approach is that it can work with images of any size. This is a bit of a technical observation, but I think important for any of you who's working already in adversarial example. Usually the adversarial example works only for a very specific image size. In here, we can work with any possible image size, and that's an advantage of the approach. Here you see the segmentation of a single person. Now I would like to show you some other examples of segmentation so you get an idea of the type of separation of the image into areas. Each area is then modified within a specific range in order to mislead the classifier. And at the bottom, you have the segmentation results, where you have people in orange, water in blue, the sky in cyan, nature, I believe, in black. And then you would have classes that are different from this as well. So if a class is none of the three, then we will apply any possible change to the color, as I will show you later on. So I don't know now with the system we're using how much interactivity we can have, but I'd really appreciate if at least the organizers would unmute themselves and play with this test I'm trying to do. So I will show you some images, and I would like you to tell me whether you think that the image I'm about to show is original or is an adversarial image. Shall we try and see whether the audio works, or at least some?
Well, I think mine works.
Okay.
Can you hear me? Okay, perfect.
I can hear very well. So I cannot see the text box at the moment. So either your opinion or the opinion of the audience, would you relay to me, please, whether you think that this image is adversarial or an original image?
I would say is original.
Looks very, very original to me.
Okay, you made my day. Thank you very much. This is an adversarial image. The original one is at the bottom. So that was exactly the purpose of the method. The idea was to generate perturbed images with a substantially large perturbation in terms of energy of that perturbation, that, however, by itself, not in a pairwise comparison, looked original. Let's try another one. Adversarial or original?
That looks to be modified, but I would say adversarial.
Okay.
Marco, what do you think?
I'm with you, Andrea Gasparin.
Okay, that is the correct estimation. In fact, the color of the clouds is a bit bizarre there, and probably in a future version of the method, we should have a more refined way of modifying those images. So the one on the top is adversarial, the one in the bottom is original. Let's try this one now. Is it an adversarial or original image?
I would say, well, it's hard to say. I would say adversarial for the grass at the bottom. What do you say, Marco?
Adversarial, I think the color of the tents maybe is a bit off.
Fantastic. You have a fantastic eye. In fact, it's adversarial, and the original one is down there. I must admit that you are the first two people who select the image correctly, so congratulations. And that gives us some more work to do in order to make those perturbations even less visible. And the last example is an obvious example of perturbation. I wanted just to make sure that you see changes we're doing. If you see this, you could think, okay, maybe they have fancy lights there because it's a party, but it's the modification of the image like that. So you see on the top, those images are images that if you pass them through a classifier are misleading the classifier. So the label of the images on the top is different from the label of the images at the bottom. However, as you can see, those modifications are relatively acceptable, especially if they are seen in isolation. And especially they are large enough for a defense not to be successful in reconvening back to the original class. So let's see some other examples here. So these are images that are modified, and those are the corresponding original images. These are images that are modified, and these are the corresponding original images. So all the images I've shown as colorful images, I go back one slide, are images that are misleading the classifier. At this point, we also wanted to do a proper subjective experiment. So we asked 39 people to look at 150 images, 150 original images, 150 images generated with colorful, and 150 generated with what was a state-of-the-art method at the time of submission of this CDPR paper. And on the right, you see the mean opinion score and the standard deviation generated from those people. 88% of people thought that the original was original. So you see that even with original images, not always people think it's natural enough to be considered to be original. And with colorful, we got 74%. So the distance between the number of people who on average thought it was original and colorful is not that large, especially not that large compared to what the other state-of-the-art method was generating in terms of adversarial images. But as you have seen with the simple test we run in this presentation, we were not still fully satisfied with what we did. And we actually wanted to take another direction, which was, can we improve an image and also turn it adversarial? And here I'm going back to the claim I made at the beginning, where I said the utility and the privacy can go hand in hand. And I will show you now the method that we developed that is going in that direction, and it's called Edgeful, which is an adversarial image enhancement filter. So the idea here is that image enhancement filters are modifying the image, and what we wanted to do is to insert the adversarial noise inside the enhancement of that image. And this is work we have presented earlier this year at ICAS. So in this case is a white box attack where we learn structure-aware perturbation, and we use a multitask loss function, meaning a function that accounts for enhancing the image, an objective that aims at enhancing the image, and the objective of misleading that image. So here is one example of image that is non-modified, and on the right you see an image that is modified with that filter. So we have modified the appearance of the image. Think of your Instagram filters you apply on your images, and within that modification, we place the adversarial perturbation, what generates the error in the classifier, in order that is not visible to a human eye. So we want the human eye to appreciate, the human visual system to appreciate the image, while at the same time that image being able of misleading the classifier. And just for those who are familiar with losses and with fully connected neural network, we are considering two losses. The first one is a smoothing loss in here, where we are learning a convolutional neural network, a fully convolutional neural network, to mimic the way you would do a smoothing. And then at the bottom here, we have an adversarial loss that works like the loss, for those of you who know about it, of the Carlini-Wagner adversarial attack that is pushing away from the logit score of the original class. So in this case, unlike colorful, we are working on the L component on the LAB color space. We do not touch the color, we just modify the luminance component, and that is what allows us to hide the perturbation through the loss here, adversarial loss, in our image. And I will show you now some exampers, and then I will conclude this part.
Just a question. Sorry for the interruption.
Sure, go ahead. Yeah.
The smoothing loss is affine to the L2 norm regularization you usually use inside in the neural networks training.
Yes.
The LS. Okay. Yeah. Thank you.
So you're trying. So there, the idea is that you want the neural network to train the smoothing. Then we have extended this to more generic filters. So the idea is that the neural network will learn a filter and then will use to generate that perturbation.
Okay, thank you very much.
You're welcome. And here is a set of examples of original images in here, and you will see the results of the enhancement of the structure in here. So these are the edge full images. So these are images where we showed how by enhancing the structure, amplifying the structure in the images, we could also trick the classifier. So again, we cast this problem into a problem of preserving the original class of the images we are sharing. But of course, you can use these very same approaches to study the robustness of the classifiers, should that be your goal. And if you want to play with that, the code of all the methods I presented so far are available in GitHub. And again, I will share with the organizers the slides so that you can have access to those should you be interested in. And as you saw, there are a number of directions that we can consider for extensions of this work. So should you be interested, please do not hesitate to get in contact with me. Now, have we got some more time?
Mark, I think we do we?
All right. Okay, so let me just tell you that there isn't only deep learning in the world. And one of the works we have done was simply looking at a Gaussian mixture model for drone videography. So when you use your drone and you take these very nice videos of a certain scene, you're likely to capture people even if they are far away. And the quality of the cameras today on nice drones are high enough that you could pass a face recognizer on those images and recognize the people you have captured. So our goal was to maintain the quality of those video, but at the same time blur when necessary the face of people such that the video itself was still pleasant to see, but the identity of people could not be inferred from the faces. So what we worked on is at a way in which we had a mixture of Gaussians whose parameters were smartly and randomly selected in such a way that they couldn't be inversed. And at the same time, this variation of the blurring was such that over time it was not jerky and therefore it was not unpleasant. And in here we used no deep learning to introduce the protection of the privacy of people, and also we consider the density of the pixels in the face of a person, and when we consider that to be low enough for a human classifier or for a machine learning classifier to be able to detect the identity of the person, we simply did nothing on that face. So this is one aspect I wanted just to touch upon to make sure that there is not only a deep learning approach to privacy, and the second one, very important, that is linking with what we said at the beginning, is about attacks on autonomous systems. We do have classifiers that are running on robots, on prototypes of self-driving cars, and these are safety critical applications. And there have been cases in which under specific experimental conditions, it was possible to apply some stickers on a stop signal in the real environment and through the sensors of existing self-driving cars, that stop signal was interpreted as a speed limit. And therefore, you can imagine that a decision on that classification result could be really critical for safety. And therefore, there is a lot of interest now in understanding how to characterize the possible adversarial attack in the physical world, in addition to the on-signal perturbation, which are the ones that we mentioned today. However, in order to apply an on-signal perturbation in a self-driving vehicles, in any forms of robots, you will need to hack that robot. And at the point, once you have hacked it, probably you don't need to add that specific perturbation. And we covered adversarial attacks for a number of sensor modalities, and especially what are the existing defenses to those attacks. And it's pretty interesting because those attacks can generate observations of objects that are not there, therefore false positives. They can hide objects. and therefore generates a false and negative detection, or they can induce a misclassification of a detected object, like in the case mentioned before. So you just transfer the categorical label from one object to another simply by appropriately placing some stickers. And this is a really interesting direction of research. In many cases, this applies only under very specific capturing conditions, under very specific angles, is not generic. But however, there are today some 3D printed objects that you can place in a scene, and a camera will misclassify as another object, or will hide a full object in that video. And that's a very, very interesting direction of research. With this, I'd like to sum up what we have covered today and go back to what we started with, that very simple classifier M that receive a signal in input X and generate a label. And I would like to conclude with maybe four direction I think would be very valuable for further research. The first one is to understand how to use those adversarial examples to train a better classifier. At the moment, if you generate adversarial examples and you're using them in the training process as well, you will lower the accuracy of the classifier. And the idea would be to maintain the robustness of the classifier up together with the accuracy, and that's still an interesting open research area. Another interesting open research area is how to look at multiple signal, like for example, not only images, but images and audios, or multiple visual modalities, and how you can make your system robust through this type of multimodal fusion of the input signal, or on the other hand, to generate attacks that are working for multimodal fusion systems. One important aspect, I think, is that of the evaluation. So all of you who are already working with machine learning are probably presenting their results in terms of mean average precision. And in terms of robustness, we want really to look at the worst case scenario, edge cases, that are really allowing us to characterize the behavior of the classifier. So the way we look at the evaluation should probably be modified in order for us to take into account the cases like the adversarial examples that are pushing the classifier off the cliff. And finally, really understanding why those adversarial examples are possible. There are a number of hypotheses going from the capacity of the classifier to the limitation of the training data, limitation in the computational resources, and the computation themselves that are available are all possible hypotheses that people are formulating in order to explain why this very successful classifier are also so brittle in terms of well-crafted examples. And certainly one interesting area of research is that of creating classifiers for which you have a certified robustness within a certain interval of any input signal. So with this, I'd like to close the presentation, but first I'd like to thank the people I presented the work of, Janice, Ali, Ricardo, and Chanje, and Omar and Apostolos. I also want to mention that if any of you is interested in a software engineer or research assistant or PhD or postdoc position, we have a number of open positions from now to the beginning of next year. So do not hesitate to get in touch. I'll be happy to have a chat with you. And thank you very much for your attention.
Well, thank you for the superb presentation, really. There are actually, we still have got time, there are a couple of questions from the audience, and I do have two questions myself if we have the time to do that. I'll go quickly through them. So Gabriele is asking, the modifications are meant to be permanent, as far as I understand. May we think to apply them just when the classifier works?
Is that referred to autonomous systems?
I might ask directly Gabriele. Gabriele, do you want to?
Yeah, maybe Gabriele, you may activate your microphone to elaborate a little bit more on your question, so that you can actually refer to say to Andrea what part of his presentation are you referring to?
Oh yes, hello.
No.
Basically, I was thinking about the idea of modifying the image. I mean, this looks great, of course, because it is useful and probably will protect the user. But let's say that you propose this kind of solution to users of Instagram. I mean, if I want to post a photo where I don't know, something is red, maybe I wanted it to be red. I mean, I want to accept a solution like this because I care more about the quality of my photo than my privacy, because maybe I just ignore what I mean, all the background of this kind of solutions. So I thought that maybe this kind of modification may be applied just when I know, but supposing that I know that the classifier works.
Yes, so I see what you mean, and you're perfectly right. However, we are operating in this case under a black box assumption, meaning that we don't know when and how the classifier operates. So there could be some use cases where, imagine a social media platform would say, we care about the privacy of users, and actually we provide you with this type of counteract from the users, not only to protect against us, but also to protect against other people who might parse those images and generate profiles about people. So that is certainly one desirable direction. And in terms of the preference you mentioned, one of the projects we will be starting early next year is exactly about involving people to understand what their preferences are. So if you're interested in, please drop me an email. I will involve you in the workshops we will be organizing with people to try and really understand how to apply what we have developed here into a user-facing application that is respectful of privacy and also is respectful of the preferences of the users.
Sure, thank you.
I get the opportunity to say, if you're organizing that workshop and you let us know, as a society, we will spread the voice. We'll be more than happy to do that.
Yeah.
And the second question is by Ricardo. I think, Marco, you already partially replied to that. And it's something that I think you already replied during your presentation, but Ricardo is asking, what about training a new classifier, adding the images modified by the adversarial? But I think you already said it during the presentation, is it?
Yes, that's correct. That's an important direction. It's called adversarial training, meaning that those images that have been generated with the adversarial noise are new training examples that are enriching the image base that is used to modify the parameters of the classifier itself. So this is something that is certainly an important direction of research, because at the moment, people have demonstrated that this increases the robustness of the classifier, however, at the cost of the accuracy of the classifier itself. So trying to understand how to modify those parameters of the classifiers, with the adversarial examples without paying in terms of accuracy is certainly a very important direction of research. Some people are now looking at the redundancy, the features, redundant features that are training the classifier in order to clean up what the classifier has learned out of the training set. So it's a more principled approach that is trying to characterize what type of features are spurious and what type of features are fundamental for the classifier to learn, so that when it's deployed, it doesn't get tricked by actually working on those spurious features.
Perfectly clear. I've got two questions quickly. So the first one is about a little game that we played, and the reason why for example, myself, I decided or I recognized that there was an image altered in an image. It was just because maybe some curve of the greens was altered, so the curve of the color itself.
Yes.
I'm talking about the RGB control. But this, it can be also made not with an adversarial attack. You can use Photoshop, or it can be the camera itself. So my question is, does it alter the classifier also this, meaning that you train the network, I suppose, with the original image, let's say with a standard, just assume a standard camera, then you modify artificially the image, but not a software engineer, but just a photographer or someone. Is it then the classifier making a mistake, or?
Well, that's an excellent question, and this is linking to one of the most critical area of involuntary adversarial examples, which is in some medical applications. So there have been cases where, and this goes beyond deep learning, it's more machine learning in general. There have been cases where people have changed the instrumentation for which they were collecting medical imaging, and then the classifier generated results that were not compliant with the initial specification. So the change in hardware and how the change in hardware is impacting the classification performance is extremely important for medical applications, that there have been a number of notable cases of this. So yes, you could try and make sure that your classifier is trained using a set of variations of the images that might mimic the way different cameras would work. Of course, this would be an empirical approach. It's much more desirable to see how actually to characterize this fragility of the classifier and understand how to make them more robust by default.
Okay, and the last question I had, if I got it right, so your idea was to identify certain regions of the pictures that are not that, in a sense, relevant. In a sense, obviously, someone is taking a picture of the sky. The sky is obviously relevant, but in the case of people and so on, okay, you're trying to do this, but the color, sometimes it can be a problem. So the exact problem that Gabriela was mentioning. So the fact that then your image is altered. But what about changing the characteristics or parts which are normally not relevant? So for example, networks can easily recognize when it's blurred something. So something is on the background and it's blurred. So identify those, or for example, black patterns, which normally our eye can confuse quite quickly, quite easily. Is it possible to act on those parts, just on those parts, so you don't change actually the picture, but at the same time have the result to mislead the classifier?
So yes, that's an excellent point. That's one of the reasons why we made the software available, is because we really want people to build on the work that was done in direction that are specific, like the one you mentioned. So I'm sure that people with a deep knowledge of photography would be able to generate some very fine filters that are also adversarials. And in particular, what you're saying, to exploit the characteristics of the human visual system, one of the direction of evolution of this work, in particular colorful, is that of not only, as we have done, generate 5 different classes. One is don't touch, one is do whatever you want, and other 3 are, well, just operate within these boundaries. The next step on this initial approach would be to be much more refined on the way you do modification. For example, you look at the type of texture you have. If you have certain type of textures, it will be much easier to hide the perturbation in there. Maybe also look at the various color components and how we are more sensitive to variations in certain color components than others. So any exploitation of the way we look at images can be embedded in the type of attacks we have developed, and it's just a matter of changing the way those color changes are introduced. So if you take the code of colorful, and you will change the functions that are generating that color by adding, for example, a model of the human visual system or a model of specific parts of the human visual system, that will generate some noise that will be better hidden inside your image. We have recently submitted an extension of the ICASP work on Edgeful that is looking at additional filters. And I'm sure that a wider range of filters can be used, especially exploiting both the characteristics of the human visual system and deep knowledge on photography.
Okay, thank you very much. Yeah, it's a super interesting topic. And I think we have the last question before we go. We'll leave the stage to Ginevra. Ginevra, don't no worries. We're not in a hurry. We started at 45, so we will carry on in case until 5:45. So there's no reason to worry. There is a last question. And I recently read the papers on adversarial attacks in neural language processing, and most of what you said
natural language processing. Sorry to
what did I
correction.
say?
Neural language processing.
Okay, neural language would be even more interesting. Natural language processing, and most of what you've said today seems to apply in that domain too. Do you think developing more robust algorithms should be a primary concern in all AI fields?
Yes, I could stop by saying yes. I will elaborate a bit on that. At the beginning, when I introduced the problem, I talked about a signal, and then I said, look, we will cover images today. In the group, we have worked on audio, and we believe that both linguistic and paralinguistic characteristics of audio are important. We have at the moment a work under review in ICASP where we have looked at this problem, and we are certainly interested also in language aspects. So how, for example, to modify it. And actually, now that you are referring to a natural language processing, adversarial attacks to machine learning probably started with natural language processing when people started to evade spam filters by providing a lot of white text on white background. So a machine would believe that that text was correct text, whereas all the spam information was in black over white. So historically, natural language processing is the area where adversarial attacks have been flourished in terms of business activity. But today, once we start having these extremely powerful machine synthesizers for language like GPT-2 and 3, we really want to be able to understand how to protect from either malicious activities or from invasion of privacy. For example, would we want to protect our conversation from digital personal assistants that are listening to us in ways that might not be acceptable? And therefore, there are a number of works with physical adversarial attacks and also digital adversarial attacks that are looking at protecting voice, spoken language, as well as text from various forms of attacks. So going back to the original answer, so yes, here we should cover all the signals. And today we looked at images because images are a really rich set of information that are describing our lives, and at times in ways that we are not really realizing. That's why we are really now looking at the amount of information that we are sharing online with images, and we are not compromising only our own privacy, but we tend to compromise also the privacy of others.
Okay, thank you very much. I think we don't have any questions right now, so we can go on with Ginevra.